Dilute Solutions Colligative Properties Part 1, presented by G. Satyanarayana Gaud, Assistant Professor, Dr. B.R.R. Government College, Jadcherla. Today we discuss about the colligative properties, types of colligative properties. In that we discuss about the relative lowering of vapor pressure, Raoult's Law, relation between the relative lowering of vapor pressure and molecular weight of the solute in dilute solution. This is the area of discussion. Let me say what is meaning of colligative property. The property which depends on the number of solute particles which dissolves in the specific volume of solvent and independent of the nature of the solute are called colligative properties. Means these properties depends only on number of solute particles. For example, a solution is containing 100 ions. There is 100 ions of solute particles. A solution is containing 100 ions of solute particles. Another solution is containing 100 molecules of the solute particles. Means in the first case, ions are acting as solute particles. Whereas in the second case, molecules are acting as solute particles. If the number of these solute particles means in first case the number of ions, in second case the number of molecules, if their number is same in specific amount of solvents in each case, then the colligative properties exhibited by those solutions, two solutions will be same. Like that is it. So colligative property means it depends only on number of solute particles and independent of nature of solute particles, means whether the solute particles are present in the form of ions or molecules or group of ions. Is it that will not influence these properties. That depends only on the number of solute particles. Number only. Is it? Next, we say the colligative properties are actually exhibited by the solvent which is present in the solution. These colligative properties are applicable to the solutions in which non-volatile solute or non-volatile solute is dissolved. Means a solute must be in solid state before preparation of the solution and solvents must be a liquid. Is it a liquid in which a non-volatile solute is dissolved? For other systems, these colligative properties are applicable. So the solute must be a non-volatile solute. Is it? So the colligative properties are the properties exhibited by the solvent molecules, and these properties purely depends on number of solute particles, and these properties are totally independent of nature of solute particles. If the solution is a dilute solution, that is for ideal solution, in order to measure the actual colligative property, the solution must be the ideal. In that case, we will see the actual properties. We can observe actual colligative properties. Is it clear? So colligative property means the property which depends on number of solute particles and independent of nature of solute particles. First point. Second point is these are the properties exhibited by the solvent of the solution. Third one, the solute must be a non-volatile solute and solvent must be present in the form of liquid states. So these properties are actually accurately observed in case of the solutions which behaves ideal. Means generally a dilute solution, very dilute solutions will behave as ideal. This is meaning of colligative property. Types of colligative properties. 4 types of colligative properties are there. One is lowering of vapor pressure. Second is osmotic pressure. Third is elevation of boiling point. Fourth one is depression in freezing point. So, except osmotic pressure, remaining can be easily understood very easily. How you see? First one is lowering of vapor pressure. Means when a non-volatile solute is dissolved in liquid, the vapor pressure of that liquid will decrease. That is the meaning. Lowering of vapor pressure means vapor pressure will becomes lower, less than the first case. Means when the solvent is present in pure state, that is the first case. What is the second state? The second state is in that solvent we are dissolving a non-volatile solute. If you dissolve a non-volatile solute in that solvent, what happens? The vapor pressure of that solvent decreases. That is the first case. Osmotic pressure that we discuss in later. Let me see. The remaining can be easily understood. What is the third one? You see, elevation of boiling point. Means when a non-volatile solute is dissolved in a solvent, liquid solvent, what happens? Its boiling point will increases. That is meaning of elevation, increase in boiling point. What is the fourth one? Depression of freezing point. When we dissolve a non-volatile solute in solvent, what happens? The freezing point will decreases. It will lower. It is called depression of freezing points. All these phenomena we can observe. We can observe. All of these properties can be studied experimentally. So this is due to only the addition of or dissolving non-volatile solute in liquid solvent. Because of this only we observe all these properties. That are the types of colligative properties. 4 types we say. So we'll discuss each and every property in detail. Today we discuss about the lowering of vapor pressure and relative lowering of vapor pressure. From that we derive the Raoultts law. Let me see that. Lowering of vapor pressure. At a given temperature and pressure, the addition of non-volatile solute to a solvent results lowering of vapor pressure. Just now we said is it. Due to addition of non-volatile solute, the vapor pressure will decreases. Why the vapor pressure decreases? That you have to see. Here 2 diagrams are given here, 2 different situations. One is, this is the first case, we are observing a pure solvent. This is a pure solvent. Suppose let's say water, pure water. So it contain only the solid molecules. It is a closed container also. At given temperature, what happens? The solvent, liquid solvent molecules will evaporate to fill the space present above the liquid. The space will be filled by the liquid, is it? Okay. So here you see this is the space where we observe the vapor molecules. All these are the vapors, is it? At a given temperature, what happened? Due to evaporation of that liquid, the space which is present above the liquid will be occupied by the vapor molecules. So that what happened? These vapor molecules will exert pressure on surface of the liquid. So when a liquid vapor equilibrium takes place, what is the meaning of liquid vapor equilibrium? Means the rate of evaporation when becomes equal to rate of condensation. Rate of evaporation becomes equal to rate of condensation. That state is called liquid vapor equilibrium. At that state, the pressure exerted by vapor of a liquid on surface of the liquid is called vapor pressure. All of you know that the vapor pressure is a function of temperature. It depends on the temperature. As the temperature increases, rate of evaporation increases. So the amount of vapor which accumulate on surface of liquid also increases. So that vapor pressure increases. So as the temperature increases, the vapor pressure increases exponentially. It increases exponentially. So at a liquid vapor equilibrium, the pressure exerted by vapor molecules on surface of liquid is called vapor pressure, and vapor pressure is a function of temperature. Next, in this pure water, now we are dissolving a solute. This blue color dots are representing the solute particles. When a solute is dissolved in a non-volatile in a liquid solvent, what happens? It will homogeneously distribute in the solution. It will homogeneously distributed in the solution, so that what happen? A solution will form. Under this condition, the surface of the solution will contain now two types of particle. One is the solvent, second is the solute. Solvent molecules as well as solute molecules. Whereas the solvent molecules are able to evaporate, but solute molecules are not. Solute particle, because they are non-volatile, they will not evaporate. They will not evaporate. Only the solvent molecules will evaporate. So if you observe the surface of the solution, it is containing two types of particles. Means some places of the solvent are occupied by the solute particles, so that the number of solvent molecule decrease on the surface of the solution because of the decrease in the number of solvent molecules in the surface. So rate of evaporation also decreases, so that vapor pressure decreases. So when we dissolve a non-volatile solute in a liquid solvent, then vapor pressure decreases. If the pure solvent and a solution containing non-volatile solute, if they are present at same temperature, if these two are present at same temperature, the pressure exerted by the pure solvent is, suppose it is represented by P naught, and the pressure exerted by, or the vapor pressure observed in the case of solution, if it is represented by P, which is greater? P naught is greater than P. So when a non-volatile solute is dissolved in a solvent, what happens? The vapor pressure decreases. So compared to P naught, P will be less. So due to addition of non-volatile solute, what is happening? Vapor pressure is decreasing. So that phenomenon we call as lowering of vapor pressure. So what is the amount of lowering of vapor pressure here? P naught minus P. The difference between the vapor pressure of a pure solvent and the vapor pressure of the solution at given temperature is called lowering of vapor pressure. That is the meaning of lowering of vapor pressure. Why the vapor pressure decreases? Due to decrease in rate of evaporation in case of solution. Why the rate of evaporation decreases? Because the surface of the solution will contain solvent and non-volatile solute particles. So only solvent molecules will undergo vaporization. Compared to the pure solvent, the number of solvent molecule present per unit surface area will be less in case of solution. That's why rate of evaporation decreases. So vapor pressure decreases. Like that, the lowering of vapor pressure means it is the difference between the vapor pressure of a pure solvent and the vapor pressure of the solution present at a given temperature. This is one of the important concept you have to see. So as the amount of solute increases, as the amount of solute increase in the solution, then what happens? The number of solvent molecule present on the surface of solution will further decreases, because most of these places on surface of the solution, not only the surface, it will be distributed homogeneously throughout, but if we observe the surface, so number of solvent molecules further decreases, so rate of evaporation decreases, so lowering of vapor pressure increases. Means as the number of solute particles increases in the solution, what happened? The P naught minus P difference will increase. So lowering of vapor pressure is directly proportional to, we say, concentration. So 1 m concentration of solution, same solution, but if it is 0.1 m, in which case we see the more lowering of vapor pressure. In 1 m concentration, we see more lowering of vapor pressure. Because the number of solute particles are more. That's why we say the lowering of vapor pressure is a colligative property. Why it is colligative property? Like that we can give the answer. Because it purely depends on number of solute particles. As the number of solute particles increase, the amount of lowering of vapor pressure also increases. That we can prove mathematically. Okay. Next we see the graph, vapor pressure versus temperature. The first curve is drawn in case of the solvent, whereas solution containing non-volatile solute. This is given for the that is represented by second curve. So at any temperature, at same temperature, suppose this temperature we have opted. At this temperature, you can see the vapor pressure of solution, it is P. Vapor pressure of solution is P. Whereas the vapor pressure of solvent, if you see, here the vapor pressure of solvent means pure solvent, it is, we say this point, it is P naught. Which is greater? P naught is greater than P. So the difference between these two, this part is it, difference between P naught and P, this one, this amount. Difference between P naught and P is called lowering of vapor pressure. Graphically, we can explain the lowering of vapor pressure. What is meaning of lowering of vapor pressure? This is P naught minus P is called lowering of vapor pressure. So always the vapor pressure curve of solution will be in the lower position compared to the vapor pressure of the solvent. Is it? So that is a situation we can see, that is it. So this is a graphical representation of vapor pressures of a pure solvent and solution. So what happens when a solute is added to the solvent? This is what to think. So two things we can observe. One is the vapor pressure of solvent decreases. Just now we have discussed. The second one is the chemical potential of solvent also decreases. Chemical potential of solvent also decreases. So when a non-volatile solute is added to solvent, what happens? The vapor pressure of the solvent decreases. The second one is the chemical potential of solvent also decreases. What is meaning of chemical potential? It is a new term to you. What is meaning of chemical potential? It is a contribution per mole of a particular component of a mixture to the total free energy of the system under given conditions of the constant temperature and pressure. That means when a system is presented constant temperature and pressure, and the system is containing some number of components. Now what is meaning of chemical potential? It is the contribution of each component, because the system is containing n components, we said. Each individual component will contribute something, some free energy to the total system. So the contribution of each of the components per mole towards the total system, contribution of each of the component per mole towards the total free energy of the system, is called chemical potential. So every component in the system will contribute some free energy to the total system. Means the free energy of total system is now nothing but it is sum of free energies contributed by the individual components which are present in that system. So we can represent like this, you see, at constant temperature and pressure, is it a constant temperature and pressure? Here we can see that the free energy of the system will be equal to mu1 dn1 plus mu2 dn2 plus mu3 dn3 and so on. So what is mu1? It is the chemical potential contributed by dn1 component. Similarly, mu2 dn2 and mu3. Each individual component is contributing something to the total free energy of the system. Is it? So that is the meaning of chemical potential. So for 1 mole, in order to calculate for 1 mole, let you integrate this equation, we get this one, G, total free energy of the system at particular temperature, pressure and containing n number of particles. That is Avogadro number of particles, let me say. It will be equal to mu1 n1 plus mu2 n2 plus mu3 n3 and so on, is it? Mu3 n3, so on, is it? This will be n3. So the free energy contributed by the first component, free energy contributed by the second component, free energy contributed by the third component to the total system, that is called chemical potential. So when a non-volatile solute is dissolved in the solvent, the vapor pressure of solvent decreases. The second point is the chemical potential of solvent also decreases. These two things we can observe. Let me see the derivation of Raoult's law. The chemical potential of any constants on the mixture of ideal gases is determined the partial pressure of the mixture. You see, when a system is present in the gas state and the system is containing some gases or the components, then the chemical potential of each constituent, the chemical potential of each component that will be determined by partial pressure. Means greater the partial pressure of the component gas, greater will be the chemical potential. So this is a thermodynamic equation which gives a relationship between the chemical potential and partial pressure. What is the relation? You can see here. Mu I is equal to mu naught I plus RT log Pi, where mu I is the chemical potential of ith component, mu naught I is the chemical potential of that component when it is present in pure form, where a Pi is the partial pressure of that gas in the mixture. So mu1 is equal to mu naught I plus RT log Pi. This is a relation which is given between chemical potential of that component and its partial pressure. This gives a relation between the chemical potential of that component and partial pressure in the system. Okay, so we know that the partial pressure P is equal to RT log Pi, we said, is it? So mu I is equal to mu naught I plus RT log instead of that Pi, because what is the meaning of Pi? It is a partial pressure. How can we write the partial pressure? We know the relation. Partial pressure is equal to, it's a mole fraction into total pressure. We are applying this formula here. So Pi is equal to Xi into P. What is Xi? Mole fraction of that component in the system, where P is the total pressure of the system. Partial pressure is equal to mole fraction into total pressure. That is the formula. So instead of Pi, we are writing Xi into P. So mu I is equal to mu naught I plus RT log Xi into P. So let us apply the logarithm. Log A B is equal to, we say log A plus log B, like that. Mu I is equal to mu naught I plus, it is RT log Xi plus RT log P. But you know, the system is present at constant pressure. That's why you see log P becomes constant. So this will be vanished out. It becomes 0. Now remaining equation you can observe here. It is mu I is equal to mu naught I plus RT log Xi. Mu I is equal to mu naught I means if the component is present in pure state, mu naught I always represent the chemical potential of that component present in pure state. Mu I represent the chemical potential of that component in the mixture. So the chemical potential of that component now depends on two factors. One is the chemical potential in pure state. Is it chemical potential in pure state? Second is the mole fraction. So this is very important formula you have to, or equation you have to remember. Is it? Chemical potential will be equal to the sum of the chemical potential in pure state plus RT log Xi. Right. So when a solution is prepared by dissolving a non-volatile solute, is it? So we can see a solution. Second is the vapor phase, vapor of the solution. These two systems we are observing. Means the system is containing two phases. One is the solution, second is the vapor. Now we are observing the solution. That is, in case of the solution for solvent, in case of solvent, you can write it. Solvent means always the solvent will be present in which state? Liquid state. That's why mu1L is equal to mu naught 1. Mu1L is equal to L represents the liquid state. The solvent present in the liquid state. Mu1L is equal to mu naught 1 plus RT log X1. So 1 always represented for or given for solvent. 2, number 2 will be given for solute. Here 1 means it is representing the solvent. mu1 in liquid state, that is equal to mu1 mu naught 1 plus RT log x1. X1 is the number of moles of solvent in the solution. Generally x2 will be given for solute, x1 will be given for solvent. Okay, so let you differentiate this with respect to dx1 at constant temperature and pressure. So mu1 d mu1 divided by dx1 at constant temperature and pressure, that is equal to, this will be constant, when you are differentiating it becomes 0. So what is the remaining part? It will d mu1 divided by dx1 at constant temperature and pressure, that is equal to RT by x1. Because the differentiate of log x1 will be 1 by x1. RT by x1 we get. So we are writing d mu1 equation. So d mu1 in liquid state, that is equal to RT by x1. Just you are shifting this dx1 in opposite direction. This is the equation we get at constant temperature and pressure. This can be written as d mu1 is equal to RT by x1 dx1. This is equation number 1, which is written in the case of what? In the case of solvent of the solution. Okay, let me see about the vapor. In the case of vapor state, the change in chemical potential d mu1 will be equal to V1 into dP. Change in chemical potential will depends on the vapor volume of that one. If this vapor behaves as ideal, then what is our formula for 1 mole? V1 is equal to V1 P1 or P1 V1 is equal to RT. P1 V1 is equal to RT, and V1 will be equal to RT by P1. Instead of this V1, what we write? RT by P1 for 1 mole of gas. So d mu1 for vapor phase is equal to RT by P1 into dP. This is the equation number 2. Observe what is the equation number 1? d mu1 liquid, change in chemical potential of liquid, that is liquid solvent, is equal to RT by x1 into dx1. Whereas change in chemical potential of vapor, that is equal to RT by P1 into dP. Here you remember, this is not a partial differentiation. You can write the complete differential, d is dx1 or d mu1 like this. But at equilibrium, what happened? The change in chemical potential of vapor will be exactly equal to change in chemical potential of liquid. At equilibrium, when the vapor liquid equilibrium exists in that system, the change in chemical potential of that vapor will be exactly equal to change in chemical potential of that liquid. So equation number 1 is equal to equation number 2. So according to equation number 1, RT by x1 dx1 is equal to RT by P1 into dP. So both sides you can see this RT and RT will get cancelled. Clear? RT and RT will get cancelled. Here RT and RT will get cancelled. The remaining part you see dx1 by x1 is equal to dP by P1. What is x1? We said x1 is the mole fraction of the solvent, whereas x2 is the mole fraction of solute. Let's substitute x1 is equal to 1 minus x2 because the sum of mole fractions is always equal to 1 in the system. Only two components are here. One is solute and second is solvent. The number of moles of solvent is x1. The number of moles of solute is x2. So x1 plus x2 is equal to 1. Therefore, x1 is equal to, we can write 1 minus x2. If x1 is equal to 1 minus x2, then you see what is dx1? Differentiate it. It will be equal to, differentiation of 1 becomes 0. So dx1 is equal to minus dx2. So instead of this dx1, what we can write here? Minus dx2. Instead of this x1, we can write 1 minus x2. So minus dx2 by, it becomes what? 1 minus x2. That is equal to dP by P1. Is it clear? So x1 is equal to 1 minus x2. So the dx1 becomes equal to minus dx2. Instead of this dx1, we are writing minus dx2, whereas instead of x1, we are writing 1 minus x2. Therefore, minus dx2 by 1 minus x2 is equal to dP by P1. Now, let you integrate this equation. What integration? Pressure limits are P0 to P. P0 is the vapor pressure of pure solvent, whereas P is the vapor pressure of solution. Due to addition of non-volatile solute, the vapor pressure decreases. The final pressure is represented by P. is when the pure solvent is present, what about the amount of solute? You see, X2 represents the solute. When the pure solvent is there with vapor pressure P naught, what will be the amount of solute? That is, what will be the mole fraction of solute? It will be 0 because the solvent is pure. We have not yet added the solute. When you add X2 moles of or X2, when the mole fraction of solute becomes X2 in that solution, then the vapor pressure of that solution becomes P naught, P. When the mole fraction of solute reaches to X2, the vapor pressure becomes what? P. So what are the limits? The pressure limits are, vapor pressure limits are P naught to P, whereas the mole fraction of solute limits are 0 to X2. So that equation is now integrated with these limits. Equation number 3 is integrated. This is integrated with these limits. You can see here. So on integration, integral of dx2 by 1 minus x2 becomes what? Minus log 1 minus x2. Already minus is there, that's why minus into minus becomes plus. So this value becomes equal to log 1 minus x2. Since lower limit is 0, so log 1 minus x2, that is equal to dp by p1 is equal to nothing but log p1. There we substitute the upper and lower limits. That's why log p1 minus log p naught, or you say log p by p naught. This can be also a log p by p naught or p1 by p1 naught. P1, why we are writing that one? Because it represents only the vapor pressure of solvent we can observe, not the solute. That is the reason. So log 1 minus x2 is equal to log p1 by p1 naught. Here both sides the logarithms will get cancelled. Finally what we get? We get this as 1 minus x2 is equal to p1 by p naught. But what is 1 minus x2? It is x1. Means this can be 1 minus x2 can be written as x1. So x1 is equal to finally what becomes? p1 by p1 naught or p by p naught simply. So x1 is equal to p1 by p naught. This is called Raoult's law. So what is Raoult's law? The mole fraction of the solvent in the solution of non-volatile solute will be equal to the ratio of vapor pressure of the solution and the vapor pressure of pure solvent. X1 is equal to P1 by P naught, or P1 is equal to what we can write? In case of solution which containing non-volatile solute, P1 is the vapor pressure of that solution. So vapor pressure of solution is equal to mole fraction of solvent into vapor pressure of the solvent present in pure state. This is called Raoult's law. Like this, we can derive an equation for Raoult's law with help of the chemical potential concept. So let me see the vapor pressure and mole fraction of the solvent. Now here the mole fraction of the solvent is represented by x1. Vapor pressure versus x1. It is present in the form of y is equal to mx. The vapor pressure is where y, whereas this p naught is m, where x1 is x. So on x-axis mole fraction of solvent is taken, on y-axis vapor pressure is taken. It gives a straight line passing through origin. Do you know the slope of the straight line becomes equal to P naught? It's a variation of the vapor pressure with mole fraction of the solvent. As the mole fraction of the solvent increases, vapor pressure also increases. You can see vapor pressure also increases. Means in case of dilute solution, the vapor pressure will be more. Mole fraction of solvent is more means what? Dilute solution it is. In case of dilute solution, vapor pressure will be more. As the concentration increases, mole fraction of solvent decreases in this direction. Mole fraction of solvent decreases in this direction, you can see. Then what happens? The vapor pressure gradually decreases. So this relation we can understand clearly with the help of this graph. Next, let me see the Raoult's law. How can we write this Raoult's law further? Raoult's law can be also written as x1 is equal to p1 by p. This is the actual Raoult's law. We got it. x1 is equal to p1 by p naught. But what is x1? Instead of x1, we can write 1 minus x2. Is it x1 is equal to 1 minus x2? Because x1 plus x2 is equal to 1. Already we have discussed. That is equal to again p1 by p naught. What is p1? Vapor pressure of solution. P naught is the vapor pressure of solvent in pure state. Let you multiply, cross multiplication. When you do the cross multiplication here, P naught into 1 P naught minus P naught into x2 P naught, that is equal to P1. Next, P naught minus P1, just you are shifting this position, exchanging the position, let's say, suppose this is brought to the right side, whereas P1 is brought to the left side. So P naught minus P1 becomes equal to x2 P naught, or P naught minus P1 by P naught is equal to x2. This is equation number 5, very important. So what is meaning of P naught by P1? P naught minus P1. What is the meaning of this P naught minus P1? It is lowering of vapor pressure. The lowering of vapor pressure divided by the vapor pressure of solvent. Here you are calculating a ratio. The ratio between the lowering of vapor pressure and the vapor pressure of pure solvent. That is exactly equal to the mole fraction of solute, which dissolved in the solution. So Raoult's law can be defined like this, is it? It can be defined like this. How can we define? The vapor pressure of a solution is equal to, vapor pressure of the solution is equal to, it is a product of mole fraction of the solvent and the vapor pressure of the solvent present in the pure state. That is one of the form of the Raoult's law. So the Raoult's law can be also defined like this also. What is Raoult's law? Actually, this P naught minus P1 divided by P naught is called as relative lowering of vapor pressure. So the relative lowering of vapor pressure of a solution containing non-volatile solute is equal to mole fraction of solute. RLVP we say. RLVP of a solution is equal to mole fraction of the solute. That is nothing but the Raoult's law. Define Raoult's law. So this is a definition. Relative lowering of vapor pressure of a solution containing non-volatile solute is exactly equal to mole fraction of solute. This we call it as Raoult's law. You remember the relative lowering of vapor pressure of any solution at any temperature below boiling point, if you see, always will be a constant. Means RLVP of a solution does not change with temperature. Where? Within the below the boiling point of the solvent. This RLVP does not depend on the temperature. At all temperature, if you measure the RLVP of that solution, it will be always constant. That is observed experimentally by Raoult's. So define Raoult's law is a very important question. The Raoult's law is defined as RLVP of a solution. RLVP means relative lowering of vapor pressure of a solution is exactly equal to mole fraction of solute. X2 is the mole fraction of solute, where X1 is the mole fraction of the solvent. So we want to determine the molecular weight of the solute with the help of RLVP. Let us see the relation between the relative lowering of vapor pressure and molecular weight of solute. According to Raoult's law, just now we have seen the Raoult's law is given P naught minus P1 divided by P naught is equal to X2. You remember P naught is the vapor pressure of pure solvent, P1 is the vapor pressure of solution, X2 is the mole fraction of solute. What is mole fraction of solute? It is the ratio between number of moles of solute divided by total number of moles present in that solution. It is a binary solution, that is it. That's why it is containing only two components. One is the solvent, second is the solute. So X2 can be written as N2 by N1 plus N2. What is mole fraction? It is the ratio between the number of moles of a component to the total number of moles present in that system. So X2 is equal to N2 by N1 plus N2. But in case of very dilute solutions, what is the meaning of dilute solution? Where the amount of solvent will be more, where the amount of solute will be less. Compared to the amount of solvent, the number of moles, compared to the number of moles of solvent, the number of moles of solute will be very less. That we can observe in the case of dilute solution. So in very dilute solution, what happens? The number of moles of solvent will be greater than the number of moles of solute. That's why the number of moles of solvent can be neglected the number of moles of solvent can be neglected compared to the number of moles of solute. So in this fraction, we can neglect N2 comparing with what? N1. That's why now this equation becomes what? You see, P0 minus P1 divided by P0 is equal to N2 by N1. Okay, so what is N2? Number of moles of solute. How to calculate it? It is nothing but weight by molecular weight. That's why weight of the solute W2 divided by molecular weight of solute M2. Remember, M2 is the molecular weight of solute. Similarly, what is N1? Number of moles of solvent. It is nothing but the weight of solvent W1 divided by molecular weight of solvent. One integer is given for solvent, 2 is given for solute. So W2, P0 vapor pressure of pure solvent, P1 vapor pressure of the solution, W2 weight of the solute in grams, M2 gram molecular weight of the solute, W1 weight of solvent in grams, M1 gram molecular weight of the solvent. So W2 by M2, here you see this part, W2 by M2, that represents the number of moles of solute, whereas W1 by M1, this part represents the number of moles of solvent. That we can see it. So with help of this equation, we can calculate the molecular weight of solute. This equation gives this is the equation which gives a relationship between RLVP and molecular weight of solute. So P0 minus P1 by P0 is called RLVP, and here M1 is the molecular weight of solute. And also you can observe here where RLVP is directly proportional to number of moles of solute. That's why we say the RLVP depends on number of moles of solute particles in the solution. That's why RLVP is a colligative property. Like that also we can mathematically prove the relation between the RLVP and molecular weight of solute. Next, we can express this RLVP in terms of molality also. What is the meaning of molality? Do you know? It is the number of moles of solute dissolved in 1 kilogram of solvent. That is 1000 grams of solvent. That is called molality. So this is the equation which gives given by the Raoultts law. P0 minus P1 by P0 is equal to W2 into M1 divided by W1 into M2. Just now we have discussed. But what is the meaning of molality? Weight of the solute divided by molecular weight of the solute. It is nothing but number of moles of solute into 1000 by W1. Where W1 is expressed in grams here. And W1 is expressed in grams, here we have to put the 1000. This is the formula for what molality is. Molality formula. Weight by molecular weight into 1000 by weight of solvent. W1 is the weight of solvent. W2 is the weight of solute. M2 is the molecular weight of solute. Okay, so let me write this case. P0 minus P1 divided by P0 is equal to, this is not correct, is it? So P0 minus P1 divided by P0 is equal to, let to delete this. Okay, P0 minus P1 divided by P0 is equal to W2 by M1 into W1 by M2. Let you multiply with 1000 and divide by 1000. After multiplying and divide by 1000, and you observe this fraction. How you see? You observe this one. 1000 W2 by M2 W1. 1000. Next one is W2 by M2. Next W1. Means in this equation, the rounded parts terms together represent what? Molality. So this can be replaced by molality. That's why we write it. How we write? You see, P0 minus P1 divided by P0 is equal to M molality instead of this rounded part into capital M1 divided by 1000. What is M here? Molality of solution. Molality of solution. What is capital M1? Molecular weight of solvent divided by 1000. This is a relation between the RLVP and molality of solution. RLVP and molality of solution. What is the relation between the RLVP and mole fraction of solute? The mole fraction of the solute is given by this one. RLVP is equal to mole fraction of solute. From that, we are introducing what? In that equation, we are introducing the weights and molecular weights. And again, we are representing The molality term, we are introducing molality term in that. So P naught minus P1 divided by P naught is equal to M into capital M by 1000. RLVP is equal to molality into molecular weight of solvent divided by 1000. This is a relation between the RLVP in terms of molality. Like that, we have discussed what is meaning of colligative property. So which type of solutions will exhibit the colligative properties. Second point, types of colligative properties. In that, we have discussed the relative lowering of vapor pressure. Why the vapor pressure decreases on dissolving non-volatile solute in it, and relation between the lowering of vapor pressure and concentration, and derivation of Raoult's law based on the concept of chemical potentials. After deriving that, what is the relation between the RLVP and the weights, molecular weights of the solute and solvents, and the relation between the RLVP and molarity. These things we have discussed. Okay, next class we will solve the problems on it. Thank you.